Good morning and welcome to Argonne National Laboratory's Frontiers in Materials Manufacturing, Materials for Water. Just a few logistical notes before we get started. BlueJeans works best in the Chrome browser, so if you connected using another browser, you may want to exit and reconnect with Chrome. Your microphone and camera were automatically turned off when you joined the webinar. If you have questions related to the technology of this webinar, for example, if you can't hear or see the presenters, or the presentation, use the moderator chat feature and a member of the Argonne team will help you troubleshoot. This private chat may be accessed by clicking the icon that looks like a talk bubble. Public group chat has been disabled for this event, but we do look forward to engaging you during this webinar, so please ask questions throughout. To ask questions, use the Q&A function, which is a square icon labeled Q&A. You can use Q&A at any time to pose new questions or upvote questions asked by other attendees. By upvoting or liking a question, those moderating the questions will be able to see which are most popular and of most interest to today's participants. Argonne would like to acknowledge Manufacturing Day, celebrated annually on the first Friday in October. Manufacturing Day is an initiative of the Manufacturing Institute, with the Fabricators and Manufacturers Association as a founding partner. Argonne is proud to join the nation's manufacturing community in showing the reality of modern manufacturing careers and addressing collective challenges to help communities and future generations thrive. Again, welcome to Argonne's Frontiers in Materials Manufacturing, Materials for Water.
Good morning, happy Manufacturing Day. Thank you for attending the first webinar in Argonne's Frontiers in Materials Manufacturing series. I'm Junhong Chang, the lead water strategist at Argonne National Laboratory. I also have a joint appointment at the University of Chicago as a professor of molecular engineering. I'm so pleased that you joined us this morning. We'll be talking about materials for water and the various ways we can help solve the world's problem, water problem. We'll be talking about materials for water and the various ways we can help solve one of the world's most pressing problems, the availability of clean water. In the next decade, 40 U.S. states will face some kind of water scarcity. To solve this problem, we need a diverse set of solutions. We'll be hearing from a group of experts about this and how materials play an essential role. We'll learn how materials can help find contaminants in water, remove those contaminants, transport water efficiently, and reuse water after that's being recovered. Argonne has been at the forefront of water research and innovation for years. Scientists here pursue work that extends from basic research discovery to scale-up manufacturing techniques that bring new technologies closer to market. Scaling up techniques is a critical challenge that scientists at here are helping to solve. Scale up doesn't mean just making more of a material. It refers to developing industry-ready processes for manufacturing the material on a large scale. Businesses see scale up as a bottleneck because it can add delays. So scientists here funded the Manufacturing Engineering Research Facility, also known as the MURF. Here, our goal is to reduce uncertainty and lower the risk for the private sector, especially small businesses. To do this, we also study new methods to make complex materials. Our success comes from novel equipment, such as the flame spray pyrolysis machine, which can create nanomaterials in a single step. But more importantly, our people make the difference. Scaling up materials is tough to learn sometimes at the university or even at the national lab. Scientists learn these skills on the job in the private sector. That's where most of my colleagues in the MURF came from. And that's why our focus today is on industry. At the MURF, we have partnered with nearly 60 companies. I'm excited to introduce industry experts who will describe their experience working side by side with scientists here. Our agenda is threefold today. First, we'll hear from Katie Kohoff, the co-founder and CEO of Numix Materials. Next, Melissa Klembara from the U.S. Department of Energy will introduce a panel of experts on water from private companies, academia, and other national laboratories. The experts on today's panel will ask how we can push the boundaries of water materials with artificial intelligence. And finally, I'm excited to kick off a virtual tour of the expanded MURF. The new MURF is more than double what it was before. When it opened in 2012, it was over 11,000 square feet. Now, the building currently occupies about 28,000 square feet. On the tour, we'll follow three guys who are scientists doing exciting materials work here: Yuepeng Zhang, Trevor Duenio, and Jeff Ila. And with that, let's get started. Our first speaker is Katie Kohoff, co-founder and CEO of Numix Materials. Katie is a chemical engineer who came to Argonne in June 2019 to grow Numix Materials as part of the lab's Chain Reactions Innovations Program, or CRI. This two-year incubator program helps entrepreneurs and startups reduce technology risk and shorten their time to market. As Katie will explain, she formed Numix Materials to develop commercial water treatment materials that can remove heavy metals from water. For more than a decade, Katie has focused on chemical process safety and analyzing process performance. Her career has been built around protecting communities and the environment through safe handling of toxic materials. She earned bachelor's degrees in Spanish and chemical engineering from the University of Kansas and is completing a Master of Engineering Management degree at Northwestern University. Please help me welcome Katie Kohoff to the webinar.
Oops. Hi, Katie. Unfortunately, we can't hear you. Can you try unmuting your microphone? Unfortunately, we still can't hear you. Can you try signing in and signing out really quick?
Katie, if you go to the menu on the top right of your screen and click Settings and check to see if your headset got reset and it's maybe connecting to your computer audio. Thanks for everybody's patience. It looks like Katie is going to try quickly logging out and logging back in. She'll be back in a moment.
Now, are you able to hear?
Yes, we can hear you now, Katie.
Yes, we can.
Perfect. Thank you, everyone. Thank you so much. Let me give my screen share another try. And without further ado, thank you for bearing with me with that. Thank you for the kind introduction, Jun Hong, and thank you for the invitation to speak today. I want to say good morning to those of you in the US and good afternoon or evening to those of you joining from other parts of the world. I'm so delighted to be with you here today to talk about something I'm very passionate about, which affects us all in seen and unseen ways every single day. The water we rely on for health and sanitation, for our businesses, the products that we use and love, and for our recreation and relaxation. As Jun Hong mentioned, I lead the team at Numix Materials, where we're creating sorbents to solidify dissolved critical metals from waste streams to enable a fundamental shift in treatment regimes. Where I'd like to go today is through a brief overview of the company and our technology, how we think about material design, manufacturing, deployment, and the interrelation among those things, and how we're putting that into motion in partnership with Argonne and MRF. And finally, I'd like to share some of the excellent resources available to industry collaborators through Argonne and the Department of Energy more broadly. So in this complete misrepresentation of the timeless phrase, I would like to start by submitting to you that there is truth in water, and that what hides for a time makes itself known eventually, as we're finding out with PFAS, and it also reveals information about how a particular stream has been used. For those who have been in industry, it's not uncommon to hear that any operating challenges have been engineered out, which goes for water as well, and that any unresolved challenges must be too big to solve. We often hear things like, we don't have any water problems here, or that's just the way we've always done it, to suggest that the status quo is the correct and unchangeable path. And I admit that I have fallen into this very trap myself by accepting rote tendencies as rigid truth. And what do I mean by that? In my days of being a bright-eyed young chemical engineer living atop a plentiful Ogallala aquifer, I happily drafted flow sheets, assuming water comes in from one side of the flow sheet and happily exits on the other, or appears around heat exchange equipment on an as-needed basis. What it means to thoroughly consider what water is escaped me for many years until I took up brewing beer as a hobby and began to consider what water could be. For me, in that time, it meant manipulating water quality to mimic that of any other region in the world to get a desired product. But that personal interaction with water and water quality was a powerful personal aha, as was handling the process residuals. So at Numix, we're specifically targeting process residuals to redefine water treatment. In the intervening eye-opening years, the problem of super inconveniently metal-laden water kept rearing its head. I have a feeling that a lot of people on the call may appreciate the issue and that it seems like it should be easier than it is. We're aiming to make it much easier by designing and producing high-capacity geomimetic adsorbents, taking lessons from the Earth's own ability to capture and release metals. And we target deployment of these adsorbents to water sources maybe not often thought of as such, like steel pickling liquor, like acid mine drainage, like electroplating baths, in order to harvest metals, thereby reducing the load on downstream systems, which may be designed water treatment systems or maybe natural systems that have to take that contaminant load in the absence of a better option. So finally, we recover those former contaminants for beneficial reuse in their own right, providing a source of critical metals, reducing the potential for overall harm, reducing the ensuing cost of mitigation, and increasing the overall value. We're addressing these market segments, having identified the opportunity to turn waste streams from these industries into concentrated metal byproducts, and to turn cost drivers into value drivers. Our team has been developing this idea since 2018 when we were all at Northwestern University, having met there after about 30 combined years of experience in adjacent fields with a shared problem of metal in the wrong places. In our time at Chain Reaction Innovations, we've reframed our thinking of water treatment systems to be more like residuals reactors. There's a tremendous opportunity to concentrate and harvest critical metals from contaminated water. So we're scaling production of sorbents and harvest of critical metals in order to demonstrate a circular economy business model that we're building. Moving on, talking about materials that matter and making them. For those unfamiliar, there is a new hub, NAWI hub, for desalination and non-traditional water use. And that the team has identified 5 non-traditional water sources and 4 pillars for focus of water innovation, research, and development. The highlighted in yellow areas are NUMIC's focus areas where our solution fits, not to diminish the need for solutions in municipal and agricultural fields or the need for integrated data analysis and modeling and simulation by any means, but our focus is in these particular areas. For those who are interested and unfamiliar, please do visit the website at the bottom to learn more about what NAWI is doing. And so, given that, here are a couple of ways that we think about shifting the paradigm for materials for water. First, increasing efficiency, whether that be the mass ratio of material deployed to material removed, or the volume of water used to generate water of a particular quality. Step change solutions are in fact needed in this area. Second, robustness is an increasingly desirable characteristic. Robust materials that can withstand fluctuating operating conditions, whether that be from a change in production lines in an industrial facility or from increased weatherfall due to changing climate patterns. Resilience is going to be only more desirable going forward. And finally, what else can you accomplish with the material? What happens once the material has gone through a water treatment process? A recent development out of Northwestern, for example, seeks to not only remove oil contaminating water, but also to repurpose spent materials as something like material for battery anodes, which is super, super cool. We've integrated that particular approach into the performance requirements that we specify for our materials, from the capacity to the applicable pH, metal concentration, and salinity ranges, to the number and types of environments in which they can be deployed to generate not only fit-for-purpose water, but also useful byproducts from non-traditional sources. We've taken a couple of steps to ensure manufacturability, and we're working closely with MRF to scale materials. And we look for these characteristics. First, earth-abundant feedstocks. We don't want to spend a lot of time developing a material that we're never going to be able to get the ingredients for. Moderate manufacturing conditions. Likewise, we don't want to make materials that can't be reproduced in real-world manufacturing facilities. Simplifying processes is often trickier than it seems. Sometimes intensifying them is useful, but utilizing equipment, for instance, the Taylor Vortex reactor available at MRF, is one way to do more with less footprint, for instance. And finally, we require that our materials be easy to deploy and recover, because we recognize that it doesn't matter how well you made the parachute if it can't be used when needed. So our approach is to deploy these materials for specific targets, and you can kind of view this as a timeline. So first, targeting the transition metals that are going to be required in increasing quantities for the transition to clean energy. Then the platinum group and conflict minerals next, rare earth elements, and finally, we aim to target recovery of fuel minerals and more broadly, remediation context. Through Chain Reaction Innovations, we're able to work with the Argonne scientists who have a depth and breadth of expertise to not only scale our materials, but also to analyze the performance of materials once created in various contexts. And so for those of you interested in diving into creating materials for water, first of all, do it. Absolutely, I can't encourage it enough. But I also want to make you aware of some opportunities that are available through the Department of Energy. I've mentioned a couple of times Chain Reaction Innovations, which is one of the lab-embedded entrepreneurship programs. There's the SBIR and STTR programs that are set-asides for small businesses, and there are some other Department of Energy funding opportunities more broadly, and I'll talk a little bit about each of these. First, the lab-embedded entrepreneurship programs, or colloquially LEAP programs, are 2-year cohorts that provide access to space and resources at 3 national labs. For us, this has been an incredible experience to work alongside our PIs and to use the incredible tools that are here at Argonne. Not only do you get access and the opportunity to collaborate closely, but also there's funding available to accelerate technology as well as commercialization support to bring new technologies to market. I would be remiss not to mention that all of these programs are accepting applications for their next cohorts and generally holding webinars for people who are interested in gaining more information about any of the 3. The SBIR and STTR programs are available through all federal agencies with budgets greater than $100 million per year. And STTR for greater than $1 billion. These are fairly well known in the startup community as they provide a significant source of funding. I think what's interesting to note also is that Argonne can be included as a sub-awardee. So some of the tasks can be completed by Argonne and Argonne scientists. And then also it's worth noting that the incredible technologies created at Argonne can also be out-licensed for the STTR program. Other opportunities available through the Department of Energy often encourage or require industry collaboration. A few of these include the ARPA-E program, which is somewhat similar to SBIR, but formed around specific topics. The Office of Science and EERE offer funding opportunities at different intervals. The user facilities here can often be accessed with something as simple as a proposal to use them. And finally, there are often competitions and prizes for solutions that address certain grand challenges. And with that, I want to thank you so much for your time for joining us today. I look forward to answering a couple of questions, and if we don't get to them all, please don't hesitate to follow up, reach out. I would love to talk more.
Thank you, Katie, for sharing the new mix story. It's very exciting. We have time for a couple of questions. Audience, please type in your questions in the Q&A box. Let's see what people are saying in the box now. I don't see any audience questions yet, but maybe a question from me. Katie, what are the top benefits to work with Argonne's MURF?
So the tools and the people that are the two that come to my mind right off the top. You mentioned this a little bit in the intro, but really the expertise, the level of professionalism from the people at MRF, and the broad range of disciplines represented by the staff is really incredible. And there are a number of tools, pieces of equipment for scaling all the way up to what some would call full scale and what others might call pilot scale, depending on how you view materials. But there are quite a number of large pieces of equipment useful for large scale material synthesis.
Thank you, Katie. There's a question from the audience. It seems that you may be able to recover cobalt, etc., from lithium-ion batteries. Is this correct? At least at the pilot stage?
Yeah, so we've demonstrated the ability to recover cobalt and nickel from highly concentrated solutions, so just below the upper solubility limit of cobalt and nickel in mixed solutions. So we've definitely got that on the mind.
Great. There's another question. How does the amount of toxic metal contaminants produced in these various industries compared to the amount of solvents that can feasibly be produced? Can you make enough to offset the pollution of an industry?
That's a good question. So when I mentioned moderating process conditions, we take that into account with all of the materials that we use. So our main solvent is water. And so, yeah, that's definitely something that we take into consideration when we design the process.
Excellent. There's another question. How could a company get started working with Argonne and using its facilities?
That's a great question. I would say it maybe depends on what scale the company is operating at, but one first step might be reaching out to someone working in the area that you're interested in working with Argonne and sending them an email indicating your interest and going from there.
Thank you. Thanks for everyone asking the questions this morning. It's now time to move on to the next part of our agenda. But please know that Argonne staff will follow up with anyone whose question was not answered. Now, I'm pleased to introduce Melissa Clambara, who will moderate our panel of experts and pose questions about the role of artificial intelligence and how it may transform the manufacturing of water materials. Melissa is a technology manager at the U.S. Department of Energy's Advanced Manufacturing Office. Melissa is managing the National Alliance for Water Innovations on NAWI, a $100 million early-stage research and development group that aims to create clean water technologies. Members of this group include 3 national labs, along with more than 180 companies and organizations. Melissa is also co-leading efforts in 2 areas of the Department of Energy, its Advanced Manufacturing Office and its Bioenergy Technologies Office as part of the Plastics Innovation Challenge. She holds a bachelor's degree in chemical engineering from the University of Maryland, as well as 2 master's degrees from Heriot-Watt University in Edinburgh, Scotland. Please help me give a warm virtual welcome to Melissa Clambara.
Thanks, Junhong. Can you hear and see me?
Yes.
Okay, great. Yeah, so it's great to be here. I think Katie did a really great job of actually plugging some of the work that the Department of Energy is doing, and specifically the National Alliance for Water Innovations. So I'm excited about the discussion that we're about to have on thinking about artificial intelligence for materials for water, but also kind of writ large for energy water nexus and our water infrastructure and the types of ways that we can use AI for improving the current water infrastructure and reducing the energy intensity of water, and what the future of our water infrastructure could look like. Because as mentioned, water security and water stress is becoming more of a serious issue in the United States. And that's why the Department of Energy has interest in this area, because we use water for energy extraction, as well as in our manufacturing of materials and processes like beer. And we need water. People need water. So this is something that the Advanced Manufacturing Office of the Department of Energy has gotten more involved in. And I'm looking forward to the discussion on this panel to find out more ways about how we should think about AI and future investments in innovation. And something that Katie mentioned was that, the Department of Energy is doing a lot of different, prizes and R&D in this space. And one kind of stop shop you can go to learn more is the Water Security Grand Challenge website, which sort of lays out all the different prizes and R&D that's going on as we try to achieve the reduction in the energy intensity of water. And so, with that, I'm going to kind of tee up the panel. Each of the panelists are going to give sort of a 2-minute introduction about themselves and, how, given, the area that they work in, how they're thinking about artificial intelligence for materials for water and maybe more broadly across the energy water nexus and the different opportunities that AI can lend itself to. And then we're going to have some time at the end for questions. So please use the Q&A function. And we'll get to those at the end in the last 15 minutes. So with that, I'm going to introduce Frank Dew to introduce himself.
All righty, thank you. Melissa, can you hear me?
Yes.
Oh, perfect, wonderful. Well, thank you, and thank you to Argonne for hosting this seminar and event, and a shout out to Elena and Current for really hosting and organizing this wonderful conference. And lastly, Katie, nice job on your presentation. It's fun for me to hear a presentation like Katie's, because they are really the flip side of what we do at Cyclopure. So at Cyclopure, we're actually removing organic micropollutants from drinking water supplies. And we do that with cyclodextrin-based absorbents that are novel and really first ever uses of cyclodextrins in water. Our niche is to target micropollutants, which are a class of trace chemical contaminants, things that are at a microgram per liter and less in size, currently escape existing water treatment methods. And so there's a huge opportunity for us there to target these small compounds. We love cyclodextrins because they're renewable, derived from corn, plus their cavity size is less than a nanometer and ideally suited to by size to track and absorb micropollutants, and at the same time resist fouling by larger materials. So with that capacity, we're able to offer solutions that are cost effective because we can do things in a smaller footprint. I like to say we're kind of migrating water treatment from a mainframe to a desktop type of circumstance. I just want to give also a sense of how MRF has assisted us. In 2019, we worked with them on Scale Up, which was really critical to getting to produce the material at volumes where we could work with partners. And by virtue of that, 2020, despite all the other kind of calamities, has been a really productive year for us, both on the consumer side and with municipal and environmental partners. Having volumes by virtue of our work with MRF to get into those activities. So happy to be part of the panel.
Great, thanks, Frank. So next up, we have Peter Fisk, who I have the pleasure of working very closely with on the National Alliance for Water Innovations Hub, which the Department of Energy is funding. So take it away, Peter.
Thank you, Melissa. Can you guys hear and see me?
Yes.
Great. Next slide, please. Well, everybody, Katie did a wonderful job of telling you a little bit about this great opportunity called NAWI. NAWI rhymes with Maui, is the Energy Water Desalination Hub, and this is a new program, 5 years, $110+ million DOE investment to accelerate early stage applied research in the field of desalination. Our goal is nothing short of being able to use a wide variety of non-traditional waters. These are water types today, wastewaters, brackish groundwaters that are currently unusable or uneconomic with current treatment technologies, but could be valuable and resilient water supplies for the United States in the future. You can see the map of the United States illustrates that we have a large and thriving research community of both researchers and aligned members of the water ecosystem. Our core labs, Berkeley Lab and Relin Oak Ridge, are joined by partners EPRI, the Electric Power Research Institute, and several California state agencies, including the California Department of Water Resources, State Water Resources Control Board, and the California Energy Commission. I'll just close up by saying that one of the things we've tried to do at NAWI is to not just organize and identify the key frontier research areas to lower the cost and energy of desalination, but also to create a broad community. Our annual meeting is taking place in November 18th and 19th virtually, and our Alliance program is a $0 membership program. So you don't have to pay anything to join, and once you join the NAWI Alliance, you will get access to all our materials, our communications, our webinar library, and invitations to our meetings. So with that, I just wanted to say I'm excited to join this conversation. Thank you, Melissa.
Great, thank you, Peter. So next up on the panel, we have Elena Harkness. So Elena, take it away.
Hi, everyone. Thanks, Melissa. Great to be here today. So Current is Chicago's Water Innovation Hub. And as you heard Frank mention, we're here as part of Chicago Water Week, which also intersects with this National Manufacturing Day, and really grateful to Junhong and the Argonne team for inviting me to be part of this panel. So Current exists not because our big and complex water challenges are unsolvable, as Katie said, but because we really believe you can't tackle them alone. We like to say that Current's kind of like a Brita. No matter who you are, you can work with us and better, cleaner water comes out. So we try to solve the water by finding the best applications of things like artificial intelligence and machine learning to solve water challenges. And that really does take a lot of collaboration across sectors, across disciplines, and across geographies. So we work to build partnerships among individuals, government, utilities, nonprofit, businesses, researchers, startups. Actually, today's panel is a great example of the kinds of leaders and innovators that Current works with every day to try to help us all take more rational risks to push the leading edge of water innovation and try out new solutions. While we are an unbiased advocate for water solutions and policies, we aren't neutral. Our effort here is to try to find and advocate for the best water solutions and the ones that bring the greatest benefits for people and for our planet, starting with our backyard here in Chicago. We are Chicago-based and Chicago-focused. And we do that by trying to stay on top of the latest in water technologies. We know the field is rapidly changing, but it's folks like Katie and Frank and others that we are sort of scanning the horizon all the time, looking across the global water innovation ecosystem to try to figure out what the best solutions are that match with the problems that we're trying to solve. We also do independent assessment of those technologies. So we have engineers on staff who help us develop a database of water technologies, and then we recommend the best solutions for others to try or for us to pilot on our own. So in addition to the kinds of community and platforms that we build, like Chicago Water Week and the Third Coast Water Seminar Series and the Innovators Showcase. These are all events that you can track and follow at currentwater.org. We actually take technologies to market. So we help to create opportunities for pilots. We sometimes launch pilots ourselves. We're working on one right now that's actually tracking microbial content in the Chicago River. That's very exciting. And so all of these are ways that we try to sort of be a catalyst for water problem solving. And I'm really excited to talk about this particular question of artificial intelligence and machine learning and what we can do to sort of accelerate that going forward. So thanks, I'll stop there.
Thank you, Elena. So next up we have Paul Westeroff. Paul?
Great, thanks. So on the next slide, I'm going to, kind of represent investment from the National Science Foundation in what's called an Engineering Research Center, NEWT, which stands for Nanotechnology-Enabled Water Treatment. This is a consortium of 4 universities: Arizona State University, Rice University, Yale University, and University of Texas, El Paso. And it's a $40 million investment by our federal government. And we also have about 25 industrial partners, where what we're really trying to do is to look for material-driven innovation using nanomaterial and their unique properties to create new solutions for water purification, both drinking water and industrial wastewaters. We're really trying to use nanomaterials, and as shown here, kind of their unique properties, to move away from conventional chemical intensive processes. There's chemicals require a lot of transportation, storage, disposal, production of sludges, and oftentimes actually byproducts. So moving towards processes that can harness this entire electromagnetic spectrum provides ways to activate nanomaterials and their unique properties. Just a few quick examples, starting from left to right in this electromagnetic spectrum, we can use unique scattering properties of, even silica glass, fibers, optical fibers coated with silica nanoparticles to create kind of germicidal glow sticks that can fit in unique locations. We can, of course, put photocatalysts into solution, but we're looking at how do we mobilize photocatalysts, and actually we can increase the quantum yield or the efficiency of these by over 10x by doing this, by attaching them onto surfaces, shining UVB and UVA light on them. We also have a whole spectrum of processes, not just materials, that really go from the discovery through pilot phase that use photothermal processes and IR parts of the spectrum to harness that energy, to heat up water, whether it's doing membrane distillation with sunlight or even capturing water from the atmosphere using sunlight. So there's a whole spectrum of other unique properties as illustrated here that we're really harnessing. And NEWT is looking for advanced experimentation, but today we're going to be talking about the advanced simulation and predictive nature to design new materials, to move away from empirical attempts to estimate or guess what you think a new material with, to hopefully do it more logically through AI and machine learning algorithms. And we're really at the forefront of doing this and starting to make some fantastic breakthroughs that hopefully we'll be able to share today. Thank you.
Thanks, Paul. And I'm going to introduce our last panelist before we shift gears into some open Q&A. So Jeff Wilbur.
Hi, can you hear me?
Yes.
Great. So thanks for the invitation and the introduction. Again, I'm Jeff Wilbur. I'm a chemical engineer who went to grad school at Berkeley, during which I actually used the advanced photon source at Argonne quite a bit. I've been in industry for 12 and a half years, first with Dow and then moved to DuPont, where now I lead our reverse osmosis and nanofiltration membrane development R&D group in our water business in Edina, Minnesota. Next slide, please. Actually, that is the next slide. So we're the #1 UF, RO, NF membrane and ion exchange resin company. We're also a major supplier of membrane bioreactors. So I'm coming to this discussion with a perspective of a manufacturer on a massive scale. So let me make a quick final comment on RO and NF materials and manufacturing that drives my perspective on the opportunity for AI in this space. In roll-to-roll manufacturing of membranes, we have dozens of controlled input parameters and hundreds of uncontrolled parameters. And those inputs come together to govern an interfacial polymerization that's 90% complete in a tiny fraction of a second. But it's very difficult to measure what's going on with that reaction in real time in situ. The nature of the reaction then produces the membrane's chemical functionality, connectivity, morphology, and that relationship is really hard to quantitatively establish too. And then those polymer properties collectively produce our membrane performance, which is what we care about, what customers care about. But that final step as well, between the polymer properties and the membrane performance, is a largely unknown connection as well. So I think that the major opportunity that I see for AI in my area is to build stronger connections between all of these process inputs, whether controlled or uncontrolled, and final product properties to help influence process design or even real-time adjustment to correct for drifting uncontrolled inputs. Okay, thank you.
Thanks, Jeff. And that's actually a great kind of lead into the first question, because you touched on some specific examples of how you're thinking about applying AI and machine learning to really inform, improvements in materials and manufacturing that are used for water treatment. And maybe if you want to talk about that a little bit more, or open it up to the rest of the panel, specifically like Jeff gave an example of, how are you thinking about the opportunity of applying AI to inform research in materials or water treatment or other aspects that you're looking at AI and machine learning?
So let me add on just a little bit to my comment then. So I think that manufacturing is a big opportunity there, more than materials design in the near term for membrane materials. And AI or advanced statistical tools of various sorts would be really useful, but it's going to have to be enabled by sensors so that we can actually measure this huge array of different parameters and measure what's going on. So any sort of AI needs to be fed by the right kind of data to enable opportunities in manufacturing.
Mm-hmm, mm-hmm. So maybe building off of that, of what are some of the research barriers that you see, that maybe the Department of Energy should be investing in order to enable, the application of AI in this space?
Is this still a question for me?
Yeah, or anyone on the panel to chime in. I know, Peter, you just got done with the National Alliance for Water Innovations. You're still working through some roadmaps, but, I guess, can you talk a little bit maybe about how AI came up as an opportunity space for the National Alliance for Water Innovation?
Sure. Just want to make sure. Can you guys see and hear me?
Yep.
Good. Well, machine learning and design of materials has already shown itself to be a remarkable tool for accelerating innovation in the functioning of systems and the functioning of specific materials. Batteries is a perfect example where some of the tools used to explore a wide range of cathode compounds ended up finding some very nice high performance compounds. And Jeff, who knows how long it would have taken for the sort of traditional Edisonian process of exploration, even diligent exploration, to stumble upon these things. So it is a very bright lamp, and it has the potential to illuminate a wide range of materials and their potential properties. That being said, there are aspects to materials design and materials manufacture that might still be very elusive for machine learning and AI tools. For example, it's one thing to model the electronic band structure of materials and be able to predict equilibrium conditions. Another thing entirely to figure out whether kinetics during some multi-stage reaction are going to be easily optimized. And that's where machine learning on the basis of a large set of data, where subtle variations in synthesis performance might just yield you a rich group of end products that you can then finally back out some of the controlling variables. So these are things that that we are very excited to explore. I'd also say that the capabilities that exist in the academic sector and the national lab sector are prodigious, but this is the time more than ever that we need the guidance and collaboration from industrial partners, so that they can help us know, we looked at that and, I think you'd be better off looking over here. You don't have to tell us exactly what you're doing, but definitely try to point us in the right quadrant, and then we can go at it.
That's a really good point, Peter, and that's also another challenge because if you're looking at the manufacturing process of a major industrial player, that's one of the most closely guarded secrets. So it's going to be difficult to bridge that gap and get, say, the DOE to contribute directly to that kind of thing with established players like DuPont.
That's right. And, you know, we have to understand, I think, on the academic side, the critical importance of business sensitive and proprietary information, especially because so many aspects of the manufacturing process are not easily patented because they represent art that couldn't be easily detected in the final product. And so these end up being very, very important know-how and trade secrets. And I think that we in the research community do need to be respectful of that. That being said, when we start having projects and then suddenly DuPont starts hiring all the postdocs, we'll know that we're onto something.
Hey, Melissa, maybe just to build on what Peter was describing in terms of kinetics, definitely true, you know, at that atomistic scale. But as we saw in even some of the pictures here today, that water treatment is usually larger than an atom. And so I think there's really a need for, you know, kind of machine learning, you know, algorithms to be able to scale from that atomistic level to kind of a scale that includes things like porosity or mass transport mechanisms, because some of these are very interconnected phenomena, and these are both models, and you'd say, where's the artificial intelligence in them? Well, I think once we start doing this type of thing for one type of process, whether it's a catalyst or a membrane, I think the DOE could think of, you know, computational resources that, you know, are at a fundamental level very, you know, first principle driven that other people can start to tap into and access. And I think that would be really useful. So not everyone has to go back and think, how do I do density functional theory for an ion interacting in water, right? And so to have modules somehow that could be built upon, and that might avoid some of the proprietary nature because these would be first principle types of things.
Good point, Paul.
Melissa, I wanted to actually pick up on a word that Peter mentioned, which was illumination. So at Cyclopure, you know, we've talked a little bit about materials design and manufacturing processes. We actually use machine learning to illuminate our vision to see micropollutants in water in detection and analytics, specifically PFAS. So just to give you an example, using our high-resolution mass spec with target methods, we can see about 45 PFAS in a water sample. And so, but with suspect screening, where we apply machine learning to the data sets that come off of the mass spec, we're able to see far more compounds. So to give you an example, we had an AFFF water sample come from Michigan, and using target methods, you know, with reference standards, we saw 11 PFAS, but using our suspect methods, which we apply machine learning tools to, we saw 107. So for us in the water side, we can actually show that, you know, there's greater extent of contamination, and we can also show the performance of our materials and saying, listen, we go beyond the 7 that were identified in the target and actually pull out the 107 that are also detected by virtue of the suspect method. So machine learning is very important for us, like giving us those night vision goggles that help us see further into the liquid space. So just different than materials design and manufacturing processes.
Yeah, Elena, do you want, oh, go ahead, sorry. I was gonna just see if Elena wanted to give her perspective too on, you know, how she's thinking about AI.
Yeah, well, I was thinking about the question of getting the right expertise into the room when we know that, you know, AI is such an important tool for, as you said, illuminating water challenges. How important is it to have people who are trained up in, you know, all of the computer science techniques, but also understand enough of the chemistry or the, you know, manufacturing applications? I'm just thinking about the kind of crossover there and what the talent pipeline looks like as you know, Peter was mentioning the postdocs getting scooped up by industry. So I guess more of a question back to my co-panelists.
Yeah, maybe I can pick up on it. So at our university, we see this a lot, right? So computer science, number of undergrad students is growing, grad students, number of faculty are growing. And so what drives those computer science faculty are, really, kind of academic endeavors first and most frequently, and is how do they develop the new algorithms? And then for the subgroup of them that are interested in applications, usually applications like security, health, transportation even, come up, or, web searching, come up as the kind of first thing. And it's actually a little difficult to engage some of the faculty in computer science sometimes in water. That it's not the first thing. And they say, they ask about, how many data points are available. And they're like, well, I think I'm going to focus over here because that's a bigger scientific challenge. But I think the opportunity is really to harness these undergrads that are being trained and to understand how to engage them in the water field earlier. So I think that's a real opportunity to focus not at who are the experts, but who have skills but don't know where to apply them yet.
Yeah, that's great. And I think, Melissa, when you think about so someone like Current, where we are very, our job is to sort of connect those dots and build those bridges. That's exactly what we're trying to sort of understand, like where are some of those gaps, and then how do we think about working with, the computer science certificate programs at our public policy school here in Chicago, or other, faculty departments to sort of bring water careers, bring people who are building and using machine learning to answer hard problems in water so we've got an upstream pipeline of talent. That's a lot of where we kind of think about how to play one way.
Yeah, and I just want to add, as Paul said, you can think about that there is a union of these two communities, et cetera, and there might be a rare subset of people who occupy both. But that's really hard to find one person who has, all these things. This is why at NAUI we really emphasize the critical need for academic researchers to seek collaborators, to really come to the table not believing that you have to have all the answers, but that you have a portion of a portfolio of resources.
I just on that, want to give a shout out because I actually have two people that intersect both those worlds of environmental engineering and data science, machine learning skills. So shout out to my team. I'm lucky to have them on board.
Okay, so we have about a minute left. Are there any other final thoughts that the panel has on, the potential opportunity space in AI, and any maybe guidance for me as someone who works at DOE and, might be working on future funding opportunities in this space where you think we should really focus?
So one thing that hasn't come up is process control and water treatment plants of various sorts. So while material design and manufacturing are opportunities, I think there could be direct, immediate applications in improving the automation of processes for water treatment to handle variable feed conditions, process upsets, that kind of thing, without requiring human intervention.
I'm really glad you brought that up. I was thinking about the utility application. That's another big part of what Current does, is work very closely with utility partners. And there are, there's the technical challenges of getting the right tools in place to make that transition. And then there are the sort of human and cultural challenges of getting sort of that movement away from human controlled risk to being willing to, shift that over. And I think that's going to be a really interesting dimension of this work in the years ahead.
So Melissa, maybe just add one last thing to your question then. I think this AI revolution that's occurring is kind of reminiscent of kind of what happened with kind of the microbiome community or nanotechnology, that for the first 5 or 10 years, everyone kind of fumbles around. And so we might want to look back at those kind of trends and what were the most useful things and what led things down the wrong path. I think some of the, for the nanotechnology, some of the most useful things were, funding large buildings, funding very large investments, realizing that there was going to be failure. But, bringing this, as Peter said, bringing these communities together, but you need to provide large opportunities. And some of them might fail, but I would look back at those other kind of technologies over the last 20 or 30 years and see what worked and what didn't work from a federal point of view.
Great discussion by the panel, and I'm gonna sign it back over to Junyoung. Thanks everyone.
Thank you, Melissa, for leading that exciting discussion, and also thanks to the panelists. It's great to hear different perspectives of how AI can address water challenges. Audience, we don't have time to answer all your questions here, but please type in your question in the Q&A box. We have received a lot of questions, and our Argonne staff will follow up with you with any questions that were not answered. So with that, I would like to thank you as well. Now, I'm happy to start our virtual tour of the expanded MRF. As I've mentioned before, we recently more than doubled the size of the facility, and we have much more room to collaborate, research, validate, scale up, and design advanced materials. This allows us to work side by side with more companies, as Katie described earlier. It also lets us help others in the water industry to quickly adopt advanced manufacturing processes. I'm pleased to introduce our three guides on this tour. First, we're joining Yupeng Zhang, a principal materials scientist who oversees our new electrospinning machine. It can produce a wide range of complex nanofibers for water applications. Next, we'll hear from Trevor Zwinia, a senior process R&D chemist. Trevor will explain his long-standing role at MRF and show the equipment he uses as he collaborates with companies such as CycloPure and Numix Materials. Finally, we'll visit Jeff Elam, a chemist who funded and directs Argonne's atomic layer deposition research program. Jeff will demonstrate what we call OleoSponge, a reusable sponge that soaks up oil and could revolutionize oil spill and diesel cleanup. Now, let's get started and go to the electrospinning lab in the Materials Engineering Research Facility. All right, good morning, Yupeng, and thanks for giving us a tour of your lab.
Good morning, Jinhong. Thank you for the introduction. Can you hear me?
Yes, I can.
Okay, all right, good morning. Welcome to the Argonne's electrospinning lab at the Materials Engineering Research Facility. And I'm very happy to give you the tour. Before we go to look at the tools, I would like to introduce electrospinning technology itself a little bit. So electrospinning is a commonly used technology to fabricate nanofiber materials and non-woven structures. The advantage of electrospinning as compared to the other fabrication method is that electrospinning is a very versatile technology. It can control it can generate different materials and fiber size and shape. It can generate fibers, oxide fibers, polymer fibers, ceramic fibers, metal fibers with a size of nanometer scale to micrometer scale. And also, it can also generate heterogeneous structures such as the coil shell structures or the particle on fiber mesostructures, which are very favorable for catalysis application. Regarding to water application, electrospinning is a technology that you can generate a graded porosity of your membrane with just one synthesis step. You don't have to fabricate membranes of different sizes and glue them together. So here we have some samples of electrospinning. As you can see, we have some PVDF fibers deposited on the backsheet that was bought from Bed Bath & Beyond. And we can also have freestanding fibers. This is the PEO fibers. It looks just like plastic. So with that, we can develop a whole lot of new materials, processes, and target different applications. How does electrospinning work? So if you wanted to set up electrospinning experiment, first you wanted to dissolve your polymer into solvent. Usually we use organic solvent, but you can also use water-based solvent. And then you feed the solvent into a syringe pump, and then you can introduce that solvent through a tubing to a very thin needle here. And now you apply very high voltage to the needle, and you ground your collector that is facing the needle. In this way, you generate a strong electric field between the needle and the collector. And this electric field surpasses the surface tension of your polymer solution at the needle tip, and they pulls out the liquid out of the needle to form an elongated droplet called Taylor cone. And now if your voltage is beyond a critical voltage, then you will form a microjet from the Taylor cone. This microjet travels towards the collector in the electric field. Remember that the charged liquid, and then the solvent evaporates during this process, and you collect the dry fibers. So let's look at the real setup here. We wanted to go that way. Okay. So you can see that we have the several needles. You want to go this way? Okay. So you can see that in this setup, we have the long tubing to introduce the solution to the nozzle. And the nozzle here we use are just the regular needles, metal needles, and we have five of them right now. And so on the other side, we have a rotating drum. That is the collector that can continuously collect the fibers during the experiments. And we can move the needles left and right to generate some patterns if necessary. So as you can see that electrospinning setup is a simple process. However, to scale it up, it actually introduces a whole lot of complexity. There are two ways that you can scale up electrospinning. So the main goal is to introduce as many electrospinning events as possible. So one way is to use needleless electrospinning, where that you have a electrode and you can introduce the solvent to the surface of your electrode, and the electrode can be a metal wire, can be a rotating drum, can be a ball, so that has a large area. And then under the electric field, they generate multiple jets. Another way is to use multiple nozzles, like what we use here. We have 5 nozzles, but we have another setup that has even more nozzles here. As you can see that this is our kind of pilot line electrospinning machine, where we have 56 nozzles that are mounted on 4 bars, and each bar is controlled by a separate power supply. In this way that we can control the voltage of nozzles, and also we have the syringe pump that feeds to the bar that can come out to supply the precursor solution to the nozzles. So the advantage of that is like you can troubleshoot individual nozzles if there's a problem, and also you can introduce different materials to different syringe, then to generate heterogeneous structure to your final sample. So we can, with this setup, we can deposit on a web of 0.5 meter wide and 30 meters long. So the cool part of this machine is that we have the row-to-row setup for the web. Let me show you this spindle here. So as you can see from the spindle, that we can mount the row on one side of the spindle and then mount on the other side. So this side we will unwind the web, the other side wind the web, so we can continuously fabricate fibers just like the industry setting. So in this way, we can maximum have 3 meters per minute speed of deposition. We can control all the electrospinning parameters. For example, we can move this the plate up and down to actually adjust the working distance. We can adjust the web moving speed. And you probably notice that instead of, like in addition to this movement along the y-axis, we actually have a movement along the x-axis in this way. So that is what we call a rocking movement that improve the homogeneous of the deposition over time. So the other parameters that you wanted to adjust, you can see from the control panel that you can adjust injection rate of the solution, and you also can adjust the wattage, like here. So these interaction of all parameters that can give you the optimization of fibers. So you can see that actually when you introduce small nozzles, it's actually quite complex. There are several challenges. One is that crosstalk between the nozzles that makes the electric field distribution very complex. Sometimes you need even simulation to understand the effect. And the second thing is that when you have the high deposition rate, you need to supply the precursor solution to the nozzle tip. And when you have a thicker nozzle, like what we have here, then you have to really control the supply and the consumption of the precursor at the needle tip to make sure that you have a stable spinning process. And also you have multiple jets generation from each nozzle. And the third one is that because you use a charged solution, so the microjets actually can have repelling effect. So instead of going shoot to the substrate in a vertical straight way, they actually try to go with a separate way because of the electrical charge repelling between the jets. So to resolve all this technical challenge, we actually designed the in-situ experiment at Argonne's advanced photon cells. And to do that, we actually build a small setup that we can roll into the beamline. So this is the setup that we have here. And this is we mount the setup at Argonne APS 12 IDB beamline. So X-ray beam comes this way and passing through the needle. And here is the detector of the X-ray. So if you look at closely to this design, we actually have some special features. First, we have this needle holder that can have 6 needles to mimic the multi-nozzle fabrication process. And then we designed the collector not as a plate, but with all these thin wires. So in this way, the X-ray can penetrate through the wires, and then the nanofibers is deposited on top of the wire electrode. So the X-ray passes through the sample, but not from the electrical wire. In this way that we will not block the X-ray. And with that, we also have a design that you can see we have a step motor. After we mount this, we can actually, with this motor, this collector can move continuously from one end to the other one. The reason that we have that is with the X-ray beam position or geometry as compared to the position of the electrospinning setup, we can have a in-situ observation of nanofiber formation, or we can rotate the whole thing this way and X-ray beam cuts this way. So we have a inline process. So with that, we can we examined 94 recipes over 24 hours. So this is a typical experimental setup, the small angle X-ray scattering that we did with the setup at APS. So the small angle scattering is that the X-ray beam scattered with the diameter of nanofibers. And if your nanofiber has a very uniform size distribution, you are expected to see the oscillation of intensity as a function of the wave vector. So as you can see, we have a dark weak color and dark color and light color. So these are the scattering of your X-ray intensity when the X-ray kind of interact with your sample. However, if your sample has a large size distribution, you will not see the scattering effect. So in this way, we can, without looking at the ICM or some other ex situ characterization method of the morphology, we know immediately that we get a good electrospinning condition or not. And also with that, we can use the simulation to extract diameter and the diameter distribution of the fibers. So as I see that electrospinning can do a lot of applications. In addition to water membrane, we can also make the electrolyte, battery electrolyte, and fuel cell electrodes, some tissue engineering, air filters. For example, the air filter that we make here is we try to assemble that with the reusable master shell. So this sample here actually has the fibers on the side. The substrate is like this. So you can see it's a synthetic substrate with the fibers looks like more denser, and then you put them together to have the air filter. So there's one current that membrane technology that we use for water membrane development is called deionization membrane. So that was based on a Argonne patent, patented deionization membrane design from my colleague, Dr. Yu Pauline and Dr. Lauren Valentino. They have the invention called a resin wafer deionization membrane. So now we actually can convert the resin wafer to electrospun wafer to further increase the efficiency, the conductivity and efficiency. So
Yep, thank you. Sorry for the interruption. We are running out of time. Thank you so much for your wonderful introduction. Sure. This is a very exciting capability.
Okay, sure.
Thank you. We'll have to move on. So let's go to the Scale Up Lab. Let's see if Trevor is there.
Is everybody able to see and hear me now?
Yes, good morning, Trevor. And thanks for giving us a tour of your lab. Let's do it very quickly. Thank you.
Okay, I'll try. Welcome everybody to the Process Research and Scale Up Lab at MRF. We started this about 10 years ago with a focus on lithium-ion battery materials. And since then, we've expanded into a variety of areas, including solid-state electrolytes, nanoparticle synthesis, as well as materials more relevant to water purification, such as polymers and sorbents. I just want to quickly show you some of the instrumentation and equipment we have here. We generally start on a small scale and figure out how to run the synthesis. And then we move into larger scale equipment. Now, there is a misconception that in scale-up chemistry or scale-up processes, all you need to do is find a larger beaker or a larger flask or a larger vessel. Now, there are complications with that. Technically, they're called heat transfer or mass transfer processes. What it really means is when you run the reaction, can you control it? Can you remove all the heat generated in the process? Can you heat things up fast enough to actually get to your temperature on time? And some of the equipment we have here lets us do that and lets us measure how we're going to do stuff like this. We do have a variety of instruments such as DSCs, differential scanning calorimeters, and reaction calorimeters. And those let us figure out how much heat is generated, and then we can modify the process to make it safer. Obviously, we try to make it more economical and as practical as possible. So what you see here is one of the simple scale-up, first steps in scale-up is a 4-liter stirred reactor. Right next to it is a rotovap. Many people may be familiar with benchtop rotovaps. They do make them larger like this. It's exactly the same principle, but it does let you handle larger amounts of solvent at the same time. Further on in the process, we will scale up to 50-liter, and in the next fume hood, we have a 100-liter reactor. And it's a little in the corner here, so I'll get out of the way so you can see it. And this lets us run up to 10 to 20 kilograms of material per batch, depending on the exact process. Now, one thing you may notice is it's easy to charge stuff. We have funnels to put materials into the reactors. The challenge in some cases is getting stuff out of there. Now, most traditional reactions, especially in organic chemistry and pharmaceutical chemistry, you wind up with a solution at the end, so it's easy to pump out and transfer to your rotovap or filter dryer or spray dryer or freeze dryer or something like that. But in some cases, you want to have a solid. And that can be difficult to pull out those drain valves. One of the pieces of technology that we have is called a filter reactor, and that's in this view mode here. If you want to zoom in on that. Now this has a filter as the bottom plate of the reactor, and that allows us to isolate material directly out of the reaction. And it has a couple interesting applications that we can now isolate something cold by chilling the jacket, or we can handle things that are still hot by heating the jacket. Now that's very difficult to do if you're pulling stuff out and putting it into a standard benchtop filter or something like that. And in particular, one of our projects with Cyclopure, this turned out to be a very key piece of equipment. And having this suite of equipment here helps us and Cyclopure really hone in and develop the final process. And since then, they have actually gotten their own equipment, and they are making their own materials with this, with the technology that we jointly developed. One of the other things I want to show you, though, is something a little more newer technology. This is a micro reactor, and what this will allow you to do is you pump reagents into the reactor, they flow out, and this is particularly useful, or I can just put it on the bench here if you want. It's particularly useful for very hazardous reactions, or something that's very toxic or is otherwise difficult to handle. So at any one time, you only got a small amount of material in there. It's fairly safe, and these are actually quite scalable. Even with this tiny little chip that you saw, over a week is basically equivalent to running a 20-liter reactor. So to support all of this, we do have a suite of analytical equipment as well. It's in a different lab room, but if you want to take a look at the lab, this is sort of the rest of the lab. Obviously, we have a lot of work to do before we move into large-scale reactors. Oh yeah, the other thing I wanted to say was that with the flow reactors, those are all monitored in real time by FTIR instruments. So this is one of the sort of 3 or 4 pillars you need to really develop AI and machine learning. We can run the reactions, we can analyze them, and provide a very large data set to be optimized and number crunched by the computer programmers. I believe that finishes tour of the process scale research and scale-up lab. So I'll hand it back to you.
Thank you, Trevor. Thank you. And we don't have time to answer questions here, but we do see audience putting questions in the Q&A box. So please continue to do that, and we will follow up with you. And with that, we're now going to the final stop on our tour. Let's go to the OleoSponge demonstration. Good morning, Jeff, and thank you for demonstrating the OleoSponge. Let's do it in 5 minutes.
Yeah. Good morning, everyone. My name is Jeff Elam. I'm a staff scientist here at Argonne National Lab. I wanted to tell you about a material that we developed here called OleoSponge. OleoSponge is made to clean up oil spills in water. And what's unique about it is that we take a very common, inexpensive material, polyurethane foam, the kind of foam that you would find in a seat cushion, and we do a chemical vapor treatment to change its surface properties. The idea is that polyurethane foam by itself is not very selective. It will absorb both water and oil, and that's not acceptable for cleaning oil out of water. So what we do is a chemical vapor treatment to impart oleophilic properties, so oil-loving, and simultaneously hydrophobic. So it will repel the water and just absorb the oil. So I'm going to give a demonstration in just one moment, but I'll just mention it uses a technology called sequential infiltration synthesis, SIS. That's that chemical vapor treatment. And SIS was developed for making computer chips. So it was a completely different application, but we were able to borrow that and make water treatment materials out of it. So let me give you a small demonstration. So what I have here to begin with is just a small container with some tap water, and I have some vegetable oil, which has been dyed blue. So we're going to create a little oil spill here on the surface of the water. So there's our oil spill that we want to clean up. And then we have 2 samples. The first is just the ordinary polyurethane foam, which has not been treated. And if I place that in the oil, you can see that it doesn't pick it up. So it's just kind of
attaching to the oil but letting it go again. In contrast, this is now the oleo sponge, which has been chemically treated, and that absorbs the oil very rapidly. And you can see that it gets absorbed into the sponge. And the great thing about it is it's reusable. So once you've got the oil in the sponge, you can squeeze it to recover that oil. You might squeeze it in a different container to recover it, but I'm just doing it back here to show you that you can then do it again. So that's one of the unique properties of the oleo sponge is the reusability, and that's what makes it cost effective. So so the demonstration I'm doing here is, of course, with tiny 1-inch cubes, and you're not going to change the world with small pieces. So one of the activities that we're engaged in now is the scale up. So, how do we make a ton of this stuff? And we have different ideas for doing that, and we have a company that we're working with to try to do the scale up and the commercialization. That's one thing we're working on. The other is we've done a specific chemical treatment for absorbing oil, but there are other things you'd want to clean up from water, and we have ideas about how to put different types of coatings on this that could clean up things like, let's say, like chromium ions or these so-called PFAS, the perfluorinated alkyl substances from water. So those hopefully will be the next variants that you'll hear of after oleo sponge. So that's all I have. Thanks for watching.
Thank you very much, Jeff. Let's see if there are any questions from the audience. Let's see. Is the oleo sponge research being done in partnership with the OHM sponge developed at Northwestern?
No, this is something that was done independently. So this was actually funded by the United States Coast Guard to address things like the Deepwater Horizon oil spill. So this is a different material.
Okay, thank you. Thank you very much again,
My
Jeff.
pleasure.
So I would like to end by thanking our speaker, Katie Kohoff, and our panel moderator, Melissa Clambara. Katie, I really enjoyed hearing about your progress. And Melissa, your support on behalf of the Department of Energy's Office of Energy Efficiency and Renewable Energy is invaluable. This government investment will benefit businesses and enable U.S. prosperity and security. I'd also like to thank our panelists, Frank Castle, Peter Fisk, Elena Harkness, Paul Westerhoff, and Jeffrey Wilbur. I can't wait to see how you and your organizations will harness the power of AI to roll back the frontiers of water research. I'm grateful to everyone who joined us this morning. I encourage you to explore ways to collaborate with us at the MRF, either through its website or email address at manufacturing@anl.gov. We have exciting plans for the future, including the next episode in our webinar series, Battery Materials Manufacturing, is coming November 19th. With that, thank you again for joining us today. That concludes our webinar. Thank you.